Morning, everyone. Good morning, guys. Um, Today we are going to be looking at physics paper one, and this video, I'm going to do in a slightly different style to the previous ones. So I'm going to be working on, um, I'm going to be working on my computer, and here we have an infinite AJ. Okay, so what we're going to be doing is we're going to work through the physics paper one stuff. So I just wanted to start off today's video by reminding you guys that it's super important that you have been studying for your upcoming exams. So remember, maths. The guys that are doing maths only, there's maths on the 31st of October. Let's see, what date is there. Yeah, it's Friday the 31st of October, and then Monday the 3rd. Then we have physics on the 7th of November and Monday the 10th. So those exams are really, and you might be thinking to yourself, oh, that's not, what can we do in that amount of time? But what you want to make sure that you're doing is make sure that you're studying maths and physics every day, and any other subjects that you find tough. Maths and physics are tough subjects. You want to make sure that you study them every day. And that means a couple of things. You want to break down your practice um, into learning theory. So we've got our practice, and we should be learning theory, especially for the physics. And then we should be doing um, practical work like sums and stuff like that. And with the physics, I would say it's actually pretty much 50-50 between the theory and the practice. Some sections, well, physics and chemistry, I mean, together. The paper one stuff is more skewed towards problems, but the paper two stuff is more skewed towards theory. But throughout everything, I'd say at least like 30% of the marks come from the theory. So you want to be focusing on things like your definitions, and you also, for that, you can use flashcards, right? A good thing to do is to take the theory that you have learned and would take the definitions and write them all down on flashcards. And what you do there is you basically write the name of the rule or the name of the theory or the question on the one side, and then on the other side you have the definition. So, for example, Newton's second law of motion, and then on the back of the card you can have um, an object will remain at rest or in a constant state of motion unless acted upon by an unbalanced force. Now, an unbalanced or net force. We want to, yeah, um, a good way to use those flashcards. First of all, writing them out will help you to organize everything. When you see in an exam that there's a definition there that they haven't asked before, you can add it to your pile of flashcards as well. So if you are going through a past paper and you see a definition you don't recognize, add it to your list. And then what you can do with the flashcards is go through them, and as you get the card, try and recite the definition, turn it over. If you get it right word for word, put it in one pile. The ones that you get wrong, put them in another pile on your left. And what you'll find is that so what you then want to do is, once you get to the end of the pile, pick up the ones that you got wrong and go through them again. And then eventually you'll get to the point where you've gotten all of them right verbatim, word for word, and they're all in the right-hand pile, at which point you're done with your practice for the theory. So getting 100% for your definitions, if you're not, that will pick up your marks right away. And then some of the other sections that you want to focus on, especially for the theory, are rates of reactions, right? The Chatelier's principle, the equilibrium, reversible reactions. And especially with these two sections, you want to make sure that you have a good understanding of the differences between what are the rules for single one-way rate of reactions, and what are the rules for reversible reactions, because it's easy to get confused between the two of them. So you want to have a set of properties side by side for each of them, and that's something we'll look at when we do paper 2. So for paper 1, the main thing that you want to focus on theory-wise is going to be there's a little bit of theory in the VPM, but it's basically just like the it's basically just the idea that when an object is at its maximum height, that its final velocity will be 0, and then if an object is in free fall, that means that only gravity is acting on the object. And so that's really easy. Doppler effect, there's a little bit of theory, so you can put that down. Doppler effect, it's largely theory. About half of the marks are normally from theory. And then electromagnetism, or in grade 12 it's called electrodynamics, right? That's motors and induction, Faraday's law, the right-hand motor rule, the left-hand motor rule, right-hand generator rule. Sorry, you don't want to get those two confused, so let me not confuse you. It is the left-hand motor rule and the right-hand generator rule, and then we've also got the solenoid rule. So you want to learn all of that stuff. And then a nice one as well to focus on in terms of theory for paper 1, because we're mainly focusing on paper 1 today, is going to be the photoelectric effect. So this is something which is unfortunately glossed over at school. And not only that, but it's quite a complicated phenomenon. The idea that we have electrical potential energy being turned into light by atoms because of resonance, and then vice versa, we have gas particles that absorb light, and they then, we have metal particles that absorb light, and then they register a current in the form, and that would be your solar panels. And then the first one where the atoms are releasing light, that's fluorescence, right? So yeah, it's a good idea to watch a couple of videos on that to get a good understanding of what's actually going on. And then things like the electroscope and all the different experiments, right? Those are things that one can study and learn how to deal with as well. So then this is a good time to mention that when you are practicing the problems, right, because paper 1 is full of tough problems, you should be keeping stock of the types of problems that you've been through and the types of problems that you've never seen before, and just making sure that you make a mental note of all, or even a physical note, like in the back of a book somewhere, all the different types of problems that you've seen in the different papers. That way you'll know which ones are common, which ones are less common, which ones have only come out once or twice, and which ones are relying on some knowledge that you didn't have when you were going through the paper the first time, so that you can go back and read through that scenario. Like, for example, this is leading on from the electroscope. Another common one is the VPM section. So even when you are practicing, you should make a note of the different types of problems that you are seeing. For example, in VPM, there's a lot of different types of problems that we see. One of them involves objects that are thrown from different heights at different times. And we need to kind of memorize how to go through those questions. This is something that you can do for finance as well. Tabulate all the different types of questions and the approaches that you should be taking to the different questions, so that you're not just relying on muscle memory. It's not. There should be a mixture of the two. You should be you're practicing active recall. The idea there is that I'm getting at here is called active recall. And the idea with active recall, if you haven't looked up study techniques before, you'll see there are a lot of interesting study techniques that you can get into. Obviously, the best study technique is studying enough. So studying especially when you're preparing for exams now, make it your full-time, job. Study 6 hours a day, take breaks in between, eat right, pretend that you're training for like something competitive because you are, and then you will see results from that. So number one is just put in the effort, but then there are techniques that you can use to help improve your study time. And even if they only serve to help get you into the studying, and to help keep you consistent or to give you something to, focus on strategically, then they're also good. But um, they actually do improve your performance as well. And just like with other types of training, one technique is not going to work for everyone. So you might want to try different techniques and see which ones work well for you. Like for me, active recall is probably the best one. I find that if I make lists of things and I sit down and make sure that I take the time to recall each step or to recall all the different types of problems, then that is the first step to getting good marks. Then the next thing that I like to do is to use meta information. So meta information is basically using other pieces of information to reinforce the knowledge that you have. So when it comes to something like the photoelectric effect or electrodynamics, you can look up other things or you can watch videos that you find interesting, and the extra things that you learn will help to reinforce the fundamental principles that you've been learning in theory. So if you watch through a couple of videos as part of your sort of like less intense study time, if you just watch through a couple of videos like on Veritasium or even like Vsauce or coming out with some old school channels, but there's other channels that are also really cool. Like I like Styro Pyro as well. If you watch science and maths related content, so that's going to help to reinforce the fundamentals that you have, and also just get your brain thinking along those lines more often. So to my understanding, the way that works is, well, the best way to practice that is to try and tie the things back to the fundamentals and have conversations about those things, and you'll see where you are logically applying the principles and where you're not. But other things you can do when you are just learning a set of information is, for example, if you've got a list of reaction conditions, or you've got a number of electrodynamics rules, you will want to do things like remember how many rules are there. For electrodynamics, for example, there are 4 different rules that we use our hands to remember. There's the current carrying conductor, solenoids, generators, and alternators are generators and motors. So those 4 rules, you have to know how to use them, right? And then there's a number of other principles and stuff like that. So to be honest with you, I'm not up to date with the theory as I would want to be for an exam. And a good way to do that, a good way to get up to speed would be to go through the theory. So we'll see if we have some time, we can go and look at the theory documents, at the revision documents, and I'll show you how to go through that and, you know, focus on, you want to focus on things like the number of things that are there in the lists, which ones you find easy to remember, which ones you find difficult to remember, make a note of them. Focus on things like, and to some guys, this is going to sound like basic, but a lot of other guys, I'd say majority of learners don't do this. So you can do that as well. And then other things, sort of like more niche things like the Pomodoro technique. I think it's named after Richard Pomodoro. But basically the idea there is it's a type of periodization training where you study intensely for 20 minutes and then you take a 5-minute break. And I think that might be too long. I think the ideal time was 12 minutes and then a 5-minute break. And you do 6 sessions, or you do 5 sessions of that, and you have studied for an hour. You've had a half an hour break. But the key thing there is it keeps up your focus. So it's a proven scientific fact that we can only stay focused for a short amount of time, and that means that our attention is going to drift when people are talking. Like now, I've been going for about 15 minutes, and the stats say that like 100% of people their minds will have wandered or drifted by this point. So they're things that you have forgotten, even if you're taking down notes and writing. They're things that you don't absorb when that's happening. So that's what the Pomodoro technique is based off of. But there's lots of great YouTube content on this type of thing, specific study techniques. So that's something for you guys to have a look at. Okay, and then without further ado, let's go into the physics paper one. So again, I'm going to be focusing on the KZN um, physics paper one from 2025, because that's the main one. I am from KZN. We are from KZN, Edgeline. And all the Edgeline guys, well, you guys are also from KZN. So we are going to be going through this paper, which you wrote, and we're going to tackle the questions. It's a good opportunity for you to see what you did differently, and maybe there's some other things for you to have a look at there. Okay, so step one. Okay, the first question here is Newton's laws, obviously. I'm going to start with question two, because question one, the multiple choice, takes a long time to get through. And I would suggest doing this in the exam as well. If you guys haven't done this before, don't do the multiple choice right away, because it's a heavy going section. So you might find that some of the questions take you really long, and they're only worth 2 marks each. Another thing is that they are going to be tough questions in the multiple choice. And I find for me, it just kind of throws me off my game when I have to think about the really tough questions right in the beginning. So it's better to start off with the routine stuff. Question two is nice and routine. That way it's like the maths paper. You just jump straight into it. And if you guys are looking for a copy of the paper, just a reminder, they have it uploaded on stanfordphysics.com. Okay. So the first question here, question two, a block X of mass 6 kgs rests on a rough horizontal surface. At rest on a rough horizontal surface is connected to another block Y of mass 3 kgs by means of a light inextensible string, which passes over a frictionless pulley. So just remember, the strings will always be inextensible. That means that the force is just transferred 100%. There's no loss of force. And the pulleys will always be frictionless, or they generally are. I haven't seen a question where there's friction on the pulley, but they will tell you if there is. A force of 50 newtons is applied horizontally to block X. There it is, as shown in the diagram below. Okay, so the interesting thing here is that we've got these block Y is on top of block X, and they tell us underneath the question, underneath the diagram, sorry, the coefficient of kinetic friction between the horizontal surface and block X is 0.3, and there's no friction between the surfaces of block X and block Y. So there's no friction between the top two surfaces, or between the surfaces of the blocks, but there is friction on the bottom there. And so what's interesting here is that if we pull, and I've seen a question like this before in the IEB stuff, what happens is if you pull the 6 kg block to the left, what will happen is the 3 kg block has to move to the right. And that's because this is an inextensible string, right? So it has to stay the same length. If we pull the block X this way, the string is going to move clockwise, and that would pull the 3 kg block to the right. Okay, next, what's going to happen is we need to know that there's going to be the supplied force. Supplied force is going to have to accelerate the whole system. And then there is friction opposing the motion, but only on the bottom. Okay, only between block X and the surface. So the first thing they want us to do is draw a labeled free body diagram showing all the horizontal forces acting on block X. So that's going to be quite easy. We know with a free body diagram that we just represent the object as a dot. And then we're going to draw the forces that are acting on the block. So first of all, we've got our applied force. It acts to the right. It is 50 newtons. We've got our frictional force, which presumably is smaller than the applied force, right? Then we've got gravity acting downwards. But they only want the horizontal forces. Okay, so we won't show friction because, sorry, we won't show the normal, and we won't show gravity because those are vertical forces. So there would actually be three forces in the vertical direction. We would have gravity, we would have the we'd have the force of block Y pressing down on it, and then we'd have a normal which cancels out both of those. But another thing that you want to check here with this type of question is, do the blocks accelerate or um, do the blocks accelerate or do they move at a constant velocity? And they don't really tell us here, which is not great. You know, so if you showed the forces as equal to each other, then I mean they tell us that there's kinetic friction. So if the block is starting from rest, and then kinetic friction comes into play, then it must be the block must be accelerating. But that is that's a bit of a oversight. Then we must label these forces, right? Don't forget to label them with one of the standard labels. So FA for the applied force, and then FK, lowercase f, for static friction. Okay, so that would be an acceptable free body diagram. For 3 marks, I think that that's fine. Oh, then there's one more force that I've forgotten there. 3 marks normally means that there's going to be three forces, right? And in this case, the three forces will be tension, applied force, friction, and tension. So you can call that force of tension Ft, or you can just call it T. That's fine. But yeah, it's good to remember that because it's 3 marks, there's probably going to be three forces. So that kind of saved me there. Next, state Newton's second law in words. So we already did that earlier. I'm going to leave that out. But you guys shouldn't leave out the definitions when you go through these questions. You should be making a note of all the different definitions. And then also, if you don't know them, look them up, at least look them up on paper. If you don't know them, then what you should be doing at this stage is trying to commit them to memory as quickly as possible. Okay, next, calculate the frictional force acting on block X. So we are told that the coefficient of the static friction of the kinetic friction is 0.3, and we can work out the normal. Now this is a 3-mark question, so it should be pretty quick. We're going to start with the formula Fk equals mu k times n, where mu k is the coefficient of static friction and n is the normal. Fk is the frictional force. Now the coefficient there was 0.3, and then the normal. Now we have to remember that, and you can do a quick little sketch on the side as well, just to help yourself out. We've got the block, and we've got it's got gravity, it's got weight, right? It's got a force of gravity or a weight, and then we've got the force of the block Y, the gravitational force of block Y also pushing down on it. The normal has to cancel out both of those, so the normal is actually equal to Fg x plus Fgy, right? The gravitational force of block X and the gravitational force of block Y. Now, both of those are just going to be 9.8 times the mass. 9.8 times the mass. So for block X, that's 6 kgs, and then 9.8 times 3 kgs. But you could also do that as a single, what do you call it? You could treat them, you could just say that the normal force has to cancel out 9 kgs. So it would be 9.8 times 9. This one is not too bad because there's no angle or anything like that. That gives us 26.46 newtons. So the other thing is, don't forget the units, guys. Don't forget the units and the direction. In this case, they say calculate the magnitude, right? So In this case, they say calculate the magnitude, so that means you don't need to worry about the direction, um, just the value. Okay, but you still need to use the units. And if your answer is sorry, if your answer is negative, then just get rid of the negative sign, because negatives and positives, we only really use them for calculation. Normally, at the end of the question, you should restate your answer with the direction in words if the direction is required. Okay, 2.3.2. Calculate the acceleration of each block. Now, the blocks are going to have the same acceleration, right? So don't get confused about that. The fact that they're connected by a string means that if block X moves 2 meters to the left, then block Y needs to move 2 meters to the right in the same amount of time. So their motion is linked. The only thing that would be different about their acceleration is the direction of the acceleration. Okay. Now, when we work out a question like this, it's good to look at the mark allocation. 6 marks. That means that this is probably going to be a simultaneous question, right? We would need to make an equation for each of the blocks. The acceleration is not known, and also the tension is not known. So this is a classic type of question where um, the acceleration and the tension are two unknowns. In that case, you're going to know all of the other forces involved, or at least you'll be able to calculate them. In this case, you should be able to calculate all of them. Now, in a question like this, there is an approach called the systems method, where you can treat this as a single 9 kg object being accelerated by a 50 Newton force, and then it has a then if the only force which is opposing that 50 Newton force is friction. So you can just say 50 newtons minus the friction minus 26.46, and then divide that by 9, and that would give you the acceleration. But for 6 marks, they normally don't like that, and they'll often specify by using a system of 2 equations, which means that you're not allowed to use, or by using 2 separate equations for each object, that means you're not allowed to use the systems method where you combine them. Okay, but okay, setting up an equation for each block. For block X, first of all, we know that it has an applied force, but we always start with the formula F net equals ma. And here we're talking about block X, so we're only going to focus on forces on block X. So we've got, it's also good to make the forces that are in the direction of motion positive and the forces that are opposite to the direction of motion negative. And here we've got a 50 Newton force in the direction of motion. So let's break it down first of all. That is the applied force, right? Minus the frictional force, minus tension, which is going to be unknown because the frictional force and the tension are both going opposite to the direction of motion. And that's going to be equal to the mass times the acceleration. So we'll fill in what we know here. The applied force is 50 minus friction minus the tension, which is unknown. And this is block X, so it's 6 kgs times the acceleration. Okay, now let's just see what that gives us. 23.54. Okay, so I'm going to keep this easy, I'm going to isolate the tension. And there's 2 benefits to that. So what I can do here is bring the tension across, bring the 6A over, and minus 6A equals T. Now, the first benefit there is that I don't have to divide to get T on its own. So I'm definitely going to isolate T because of that. The other thing is that now when I substitute and I get rid of T, I'll be left with A. So it's better because they want the acceleration, they don't want the tension, but it really doesn't add too much time if you calculate the tension first by accident and then move on to the acceleration. So I wouldn't stress too much about that. Again, we start with F net equals ma. And now looking at block Y, we see that the tension is the driving force. So the tension is in the direction of motion. And now remember, even this is a situation where you don't want to say left is positive and right is negative, right? Because the direction of motion is different relative to each block. Like when block X moves to the left, block Y moves to the right. And this is common with pulley questions, even the ones where it just goes around the corner, right? If it goes around the corner, then we can say that the objects are moving clockwise. In this case, they're moving clockwise. You see, clockwise around the pulley. So anything that's in the clockwise direction will be positive. In this case, Y, the positive direction of motion is to the right because X's positive direction of motion is to the left. So if X moves to the left and we make that positive, that means that that direction on top is to the right is positive for Y. And it has no friction. So this one's going to be a little bit easier. The net force here is just T, right, equals ma. The tension, we don't know. The mass is 3, and the acceleration we also don't know. Okay. Now we've got our two equations. What we can do here is solve simultaneously. So because both sides of this equation are equal to t, right? If I take that 3a and sub it in place of t, I'm going to get 23 minus 6a is equal to 3a. And it's good to label what you've done there. So what we're doing there is we're taking equation 2 and we're subbing it into equation 1. I probably should have labeled these right. Otherwise, we don't know what equation 2 is and what equation 1 is. But yeah, again, don't worry too much about the labeling or the pedantic stuff. Focus on getting the method right. Focus on getting the answer right. The 6a is going to go across, and we will have 9a. And then we have 23.54. So let's see what that gives us. We need to divide the 9 out. It gives us 2.62 meters per second. Okay, and units, but no direction because they said magnitude. Okay, 6 easy marks. Question 2.4 is Newton's laws of gravitation. So this is where you're going to be using these two formulae. G equals M, Gm over R squared, or Fg equals Gm1 M2 over R squared. So this, it's good to just have a quick reminder, what do these formulae actually do? This gives you the gravitational acceleration. So on Earth, if you used the Earth's mass and the Earth's radius, this would give you approximately 9.8. That is the normal G that we work with. But on different planets, that gravitational acceleration is going to be different. And then the force of gravity is mg, right? Mass times gravity. So it's on Earth, again, that would be mass times 9.8. But over here, what we're doing is we're using the radius of a given planet, we're using the mass of that given planet, and then we're using the mass of the object. G is the gravitational constant, which is really huge. I can't remember what it is. G is the gravitational constant. It's small. It's 6.67 times 10 to the minus 11 newtons per meter squared per kg. Newton meters squared per kg squared. Okay. So we would just sub in value and then solve. Calculate the radius of planet M in terms of the radius of the Earth. Oh, sorry guys, just give me a second here. Okay, so a man on the surface of planet M weighs half his weight compared to his weight on the surface of the Earth. The mass of planet M is twice that of the Earth. State Newton's law of gravitation, of universal gravitation in words. So another trick that I can share with you guys, or another technique that I can share with you guys, because I don't like the term trick, but a technique to remember the laws is to look at the formula. So Newton's law of gravitation is based on this formula, right? And it says that the force that two objects that exert on each other, the force between two objects that exert a force on each other at any point in space will be directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between their centers. So you can see they're directly proportional to the ones that are on top, inversely proportional to the one on the bottom, inversely proportional to the square of the distance between their centers. So this is R value, is the distance between the centers of the two objects. Okay. All right. So let's move back onto the question 2.4.2. Calculate the radius of planet M in terms of the radius of the Earth. Okay, so this is kind of a tricky one, kind of an interesting one. You can use real values here if you really wanted to, but what they are intending here is for you to, they're intending for you to set this up in terms of the Earth's values. So a man on the surface of planet M weighs half of his weight. So the weight is Fg, right? We're going to say that his weight is half of what it was. And then they say that the mass of the planet is twice that of Earth. So if we take the mass of the Earth and sub that in as a 2, and then we look and we see, okay, the radius of planet, they want the radius of planet M. So we're going to leave the radius as it is. Now, one thing that I normally use for these proportion questions, especially if it's in the multiple choice where working is not important, is I will just sub in everything that doesn't change as a 1. So the constant obviously doesn't change, and the mass of the guy doesn't change. Now, what we want to do here is we want to take this radius of the Earth and solve for it. So first of all, I can cross multiply. I'll multiply the 2 up there, and I'll multiply the r squared up here. Two times 2 is going to be 4. And then we get the radius of the Earth to be 2. So that's really easy for 4 marks, but it's not going to be, it's probably not going to be the method that they want, unfortunately. So we'll have to come back to that one. But that's a really useful trick when it comes to, or a really useful technique for questions that involve proportions. So you can sub in the proportions of the quantities that change, and the quantities that don't change, you sub them in as 1. And that allows you to solve for the proportions of the new one. So when we get r equals 2 here, we should say that the radius of the planet is 2 times the radius of the Earth, in words, just to be 100% clear there. And so maybe that will get you 4 marks. If not, at least gives you the right answer in most of the marks. Okay, question 3 is a VPM question. So this is a type of question which is really unpopular with guys interpreting graphs, getting values from the graphs, but it's actually really easy. So let's go through it and let's see if we can shed some light on this. The first thing to know when we look at this diagram is that it's kind of upside down. It's inverted. So that means that they've taken up to be negative, and it's never a good idea if you're asked to sketch a graph like this. It's never a good idea to try and sketch it upside down like this from the start, because it looks really natural if you sketch a displacement versus time graph or position versus time graph. If you sketch it with up being positive first, then you can always flip it afterwards if you need to, if the question specifies that. up must be positive. Sorry, if the question specifies that down must be positive, then you can flip it. So a ball of mass 500 grams is projected vertically downwards towards the ground from a height of 2 meters at a velocity of 1.5 meters per second. The position time graph for the motion of the ball is shown below. So we see that it starts from a height of 2 meters. We can see that. And then it reaches the ground at T1. It's in contact with the ground from T1 to T2, and then bounces and reaches a maximum height of 0.8 meters, comes back down and hits the ground again. There is a contact time between the ball and the ground between T3 and T4, and then it has a third bounce where it reaches a height of 0.6 meters. Write down the maximum vertical height reached by the ball after the second bounce. So you're going to be very careful with this. Where is the first bounce? Okay, the first bounce is here between T1 and T2. The second bounce is between T3 and T4. The correct answer there is 0.6 meters. Right, that's after the second bounce. Bounce one, bounce two. So this doesn't count as a bounce. It's a path of travel through the air, but these are the bounces when it hits the ground. Okay. 0.6. Calculate the speed with which the ball hits the ground for the first time. Okay, so we've been given the initial velocity and we've been given the height. We don't need the time. We can calculate VF using those two. So we want to, a good way to pick equations of motion is to look at which quantities are not given and are not asked for. In this case, they don't ask for time, right? There's no time. We are given a displacement, we're given a height, and we're given an initial velocity. So we're going to use the one that involves distance only and not time. Okay, so that is the formula that we're using. Vf squared equals Vi squared plus 2a delta x. And we're looking for the final velocity. So we're going to sub in our initial velocity. Now, even like the square means that the direction doesn't really make a difference here. We need to define some kind of direction as positive. So I'm going to go with up as positive, just because I find that less confusing. If you're used to working with down as positive, it's not going to make a difference. Don't worry about it. All the signs will be the opposite. So Vi squared, it's thrown downwards. The ball is projected vertically downwards. So we're going to make that negative 1.5. And that doesn't really make a difference, right? It doesn't make a difference for our calculation because the square, when we square it out, it's going to become positive. But you must show the negative because there is a substitution mark. We've got negative 9.8 for the acceleration. And then delta x is downwards, it's 2 meters downwards. Now, you might be looking at this and saying, oh, why don't you make it positive, down positive, because everything is negative. There's nothing wrong with everything being negative. I can quickly just check and say, okay, it wasn't thrown downwards. Yes. Is gravity accelerating downwards? Yes. Did the ball move downwards? Yes. And that all makes like very easy logical sense. Whereas treating up as negative is just, I don't know. You can get used to it, but why would you want to get used to it? Anyway, let me not rant. So VF squared is going to give us 41.45, and then we have to square root to get our final velocity. We get 6.44. Okay, what is that? That's a velocity, and it is meters per second. So it will be meters per second. And is it upwards or downwards? Calculate the speed. Okay, so they say the speed. We don't need to give a direction because speed is a scalar quantity, right? If they said velocity, then we would need to give a direction, unless they said magnitude of the velocity. Next, we want the time t1, which is indicated on the graph. That's the time when it reaches the ground. Okay, so now at this point, we know the final velocity, we know everything. We can pretty much pick any equation that we want. And so I'm not going to pick this equation. Why not? Because it then becomes a quadratic when you're trying to solve for time, which is a mission. So what other options do we have? Well, we've got delta x equals Vf plus Vi over 2 delta t. And this is the best one to use here because it involves both distance and time. You could also just use, I think I might actually just use this one, Vf equals Vi plus a delta t. Now, the one thing that you will hear being said quite a lot here is to try not to use the one which relies on a value that you've calculated, because there you stand to lose marks twice. But this is a basic question, so let's not lose marks there. And then you will be fine. So the final velocity is 6.44. Vi was, okay, we've got to be careful here as well because the sign is important for this. So that's going to be down towards the ground, negative 1.5. And then we've got the acceleration, negative 9.8. And delta t. So we're going to solve for delta t here. It gives us 0.5. 0.550 seconds. Okay, cool. Next, calculate the velocity with which the ball rebounds from the ground during the first bounce. Okay, so here's a great concept if you've been doing this section for a while. If an object is thrown upwards with a certain velocity, it's going to reach a certain height, and that makes sense, right? If you want to throw a ball up in the air, the height that it goes to is going to depend only on the speed, right? You can't like throw it twice at the same speed and hope that it goes higher the one time. It's going to be directly linked to the speed with which you throw it. So we know we've got enough information there, because if we know the height, we can calculate the speed. And that's because gravity is always the same. Okay. So again, here we don't know what the time is. We don't know how long it takes to get from T2 up to its maximum height then. But we do know that its final velocity at its maximum height will be 0. So we're going to use that formula that only involves delta x again. There we go. And we know that the final velocity is 0. The initial velocity is what we're trying to calculate, plus 2 times 9.8. And then the displacement is 0.8. Okay, now let's check our signs, right? This is towards the ground, right? So it's negative. If the ball's traveling up in the air, so this is going to be positive. And then that's going to help us because this is going to give us a negative. When we bring it across, it's going to become positive. Otherwise, we'll have a problem, right? If we're trying to calculate VI and we're trying to square root a negative, our calculator is not going to like that. So that is the important part of subbing incorrectly here. 2 times 9.8 times 0.8 gives us 15.68. And then that is VI squared. So what I did there was I took this term across and I swapped the sides. And then when we square root that, we get 3.96. 3.96 meters per second. And then we'll check and see if we need to give the direction there as well. Calculate the velocity with which the ball rebounds from the ground. So did they say the magnitude of the velocity? No, they didn't. They said the velocity. If they don't say magnitude, you must give a direction. And so whether your answer is negative or positive here, what you do is you rewrite it as a positive and then say upwards. Because when it rebounds from the ground, it's going to be traveling upwards. You must give that direction in words. Okay. 3.3, calculate the force. The ball is in contact with the ground for 0.2 seconds during the first bounce. Okay, calculate the force exerted by the ground on the ball during the first bounce. So a lot of guys will sort of hit a snag here because they look at this and think, where's the force coming from? There's actually a couple of different principles you can use to calculate this. You can use Newton's laws if you calculate the acceleration, and then you use F net equals ma, right? Then you can use that to calculate the acceleration. Or you can rather you would calculate the acceleration and then use the acceleration to get the net force. Or you can use momentum. And I always recommend using momentum because it's a little bit easier. When we are using momentum for a question like this, we're going to say delta P equals F net delta T. Okay. That is the impulse equation. And then what you can do here is you combine this with the other equation, which is that delta P is equal to the final momentum minus the initial momentum, which is equal to mvf minus mvi. Or if you want to be fancy, mvf minus vi. And that is going to give us, so what I do here is I sub this in on the left-hand side. If you have a slightly different way of doing this, don't stress. Now you can see what we've got here. We've got the initial velocity, we've got the final velocity, and we've got the mass of the ball, and we've got the time. So we can sub everything in. The mass is 0.5 kgs. The final velocity is the speed with which it left the ground. We just calculated that. So let's keep that positive because it's upwards. The initial speed is the speed with which it hit the ground. Okay. And that is the answer to 3.2.1. That was 6.44. When we sub that in, though, we're going to sub it in as a negative. And the reason is because it's downwards. So, and then that is equal to F net times delta T. They say that the ball's in contact with the ground for 0.2 seconds. It's quite a long contact time. And this is what that's going to give us. We calculate, divide out the 0.2. And that gives us F net equals 26. 26 what? 26 newtons. And are we forgetting something? Force is a vector quantity. Okay, so the question now is, does the floor exert a force on the ball upwards or downwards? Well, let's think about that. The ball is coming down, it's hitting the ground, and then it's for some reason turns around and goes back upwards again. That's because the floor is exerting a force on the ball, it's pushing it upwards. Why does it do that? It does that because of the properties of the material of the ball and the surface. So, the elasticity of the ball. That's essentially why it does that, but yeah, it exerts a force upwards. But mainly because the ball has to resist the motion of the ball downwards. Sorry, the ground has to resist the motion of the ball downwards. So in order to resist that motion, it will need to apply a force upwards. And that's it. So for the next one, they say draw a velocity time graph of the motion of the ball from the time it's projected to the time when it rebounds to a height of 0.8. These graph questions are a little bit finicky. Just when you do draw them, sometimes they'll specify which direction you're supposed to take as positive. Likely they haven't done that here. But you should always draw it whichever way around feels natural to you, and then you can flip it if you need to. So they say a good thing to pay attention to is the time range. They say from the time that it's projected, so from the beginning to the time when it rebounds to a height of 0.8 meters. So we only have to go up to the second. We only have to go up to the first bounce, the apex of the first bounce, and then we need to indicate all of these times. So let's do that. Okay, we have our t-axis, time axis, and we have our displacement axis. You can make this delta x or delta y. A lot of guys like to call it delta y. And then we're going to need to start thinking about our velocities. So the initial velocity, it's first of all thrown downwards at a speed of 1.5. So I'm going to do this. It's thrown downwards at a speed of 1.5, and then it eventually hits the ground at a speed of 6.44. So I'm going to make all of the downwards distances positive. And then over here, we'll have negative 6.44. That's the speed that it reaches just before it hits the ground. Okay, and then it bounces, right? So it's a good idea to use some pencil lines here just to show, okay, we're indicating the time there where it hits the ground. And this will be the time when it hits the ground. Indicate time t1 indicated on the graph. So the time t1 is what we calculated. The time that it took to hit the ground, it was 0.5 seconds. And then the ball bounces, right? And when the ball bounces, it's now moving upwards. So its velocity is going to change direction to a positive. And a lot of guys will battle with that. So when it rebounds, its speed is 3.96 meters per second upwards. So I'm going to label that there, 3.96. Again, just marking with pencil lines nice and neatly. And it starts accelerating towards the ground. Oh, okay. Careful now. It's in contact with the ground for 0.2 seconds. So it's actually only going to leave the ground at 0.7 seconds. And so I'm going to move this across like that. And yeah, you don't need to worry too much about the pencil lines. So now it rebounds at 3.96 meters per second, but it starts accelerating downwards again and eventually reaches its maximum height where its velocity is 0. Okay. So this time where it reaches its maximum height, do we need to indicate that? No. If we did need to indicate that, we would need to calculate it because it's not something that we calculated previously. So let's just double check that we've got everything here. Time t1. Yes. Time t1. The velocity of the ball when it hits the ground for the first time. Yes. The velocity of the ball when it rebounds. Yes. So the rest of this stuff, the initial velocity, not necessary. This time 0.7, not necessary. It is very important to make sure that you always show the velocity versus time graphs with with parallel lines, right? So because these velocity versus time, because this object is in free fall, it'll always be accelerating at 9.8 meters per second downwards, and so this gradient would be negative 9.8 for any time that the object is in free fall. And so if they have the same gradient, then they must be parallel. So they'll often mark for that as well. And then another thing that they used to be super strict about, but not really that much anymore, um, units for your axes. Units for your axes. Direction defined as positive, and a title. Okay. Oh, wait a minute. No. Yeah, I'm being a noob. This is supposed to be velocity, right? And it's measured in meters per second. Okay, cool. Good save. Next, we've got um, this is going to be the momentum question. Question 4 is normally the momentum question. Um, so this is not a section that a lot of people battle with. I'm going to skip over this. I'm going to conserve my energy. I'm going to go on to the work energy and power question. Question 5. So a box of mass 7 kgs, which is initially at rest, is acted upon by a constant force of 80 newtons that's applied at an angle of theta to the horizontal. Um, so just to remind you, just to give you an idea, this is going to be W net equals delta EK, or it will be WNC equals delta EP plus delta EK. So whether you use the those are the work energy theorem and non-conservative forces. Whichever one you use in this situation, it's going to turn out the same because there is no change in potential energy here. Generally speaking, you can always use either of those two methods, and there are different ways to apply them as well. So this is a section that has a lot of application, but this is a really light work energy and power question. It's only 12 marks, and like, let's see, only 4 of those are for a tough calculation, whereas a lot of the time this will be a 20 or 25 mark question with lots and lots of calculations, like up to 8 marks per question. So yeah, let's look at this and let's get an idea of experiences a constant frictional force of 8 newtons as it moves from rest to point X. The distance is 2 meters. And as it passes point Y, it has a speed of 1.5 meters per second. So they're giving us the velocity there. And we see that it's a 7 kg block being acted on by a constant force of 80 newtons at an angle of theta to the horizontal. So it's going to accelerate because the horizontal component of the 80 Newton force is going to be greater than the frictional force of 8 newtons. Also, it's starting from rest and it speeds up to 1.5 meters per second. So we know that it's going to accelerate. What else? Well, we know that we could basically just use Newton's laws or equations of motion to work this out, but that's always true with work energy and power, and that's why they specify that you have to use energy principles only. Question 5 is normally going to be work energy and power. So what we want to do here is we want to set up, I would want to set up W net equals delta EK, and then we break down W net using the forces that we've got. We're going to need to calculate theta. So the free body diagram, I'm not going to worry too much about that. We'll just discuss it quickly. We will have gravity, we'll have the normal, we'll have the 80 Newton force, and we'll have friction. Easy. Define the term work done by force. It is the change in energy. Work is defined as a change in energy. Not really sure if that's what they want here, though. So let's look at the definition. I'm taking my own advice here. Maybe there's a definition that you don't remember, look it up, commit it to memory. Work done in an object by a constant force F is F delta X cos theta, where F is the magnitude of the force, delta X is the magnitude of the displacement, and theta is the angle between the force and the displacement. So they want you can use the formula to work that out, or you can say the work done in an object is the product of the force and the displacement of the object in the direction of the displacement. Yeah, so it's not going to be the change in energy, that's net work. Net work is equal to change in energy. That's my bad. Okay, next 5.3. So this is the one that you guys will always want to know about because it's the practical stuff. But there, up until this point, like we've had 6 marks, that's all theory. I don't want to see guys losing those marks. Okay. Question 4. Question 4. Calculate the size of angle theta by using energy principles only. Okay, so I'm just going to jump into it, and then I'll explain it afterwards. That's the work energy theorem. We expand everything. And then we break down the net force. So there's only 2 forces acting on the object here. There's the 80 Newton force, but only the horizontal component does work. So that's going to be 80 cos theta. Then we've got friction acting in the opposite direction. So you can write that as 8 cos 180. But I really don't like doing that. See, or you can just put a minus in front and say minus 8, because that is your net force. And you're allowed to do that. So I like to use this method because it is the method which is closest to Newton's laws, where we're used to breaking down the net force into the component forces that act in the direction of motion. But if you are used to putting in all the cos 180s and stuff like that, all power to you. Right, now the final velocity they tell us is 1.5. The mass is 7. Good number. And then the initial velocity is 0. It's starting from rest. So what's going to happen here is this entire term is going to fall away. Over here, we can distribute the 2. The 2 can multiply into this bracket. So it doesn't matter which order they're in. Remember, you can always take a single term, multiply it into the bracket. That's going to give you 160 cos theta minus 16 equals 7.9. This term, when we work it out, we get 7.9. And then we'll bring the 16 over. So we'll have cos theta is equal to 7.9 plus 16 over 160. Now, fun fact, in physics, they don't allocate any marks for the working steps. So they'll allocate a mark here for the substitution. But they won't allocate any marks on your way down to the answer. They are only going to allocate a mark for the final answer. So for theta here, if you have the white calculator or the old silver calculator, the FX991 Casio, then you will be able to use the equation solving feature on your calculator to just solve this and go straight to the answer. Okay. If you're not sure how to do that, you can just look up how to solve equations using Casio FX 991 ES or FX 991 ZA, whatever your calculator is called. And then you will see a tutorial there on how to fill in X on the calculator and solve for an unknown. But this is going to give us inverse cos. So if you don't have the equation solving calculator, what I did there was I brought the 16 over, it becomes a plus, divide out 160, and then to get theta on its own, we have to inverse cos. So it's going to be this. Inverse cos of that. Let's see what that gives us. 81.41 degrees. Now that seems a little bit suspicious. So I'm just going to double check something here. Okay, also this is going to give us 7.875. You don't want to round off until the end. Okay. Yeah, so it's 81.42 degrees, which seems a little bit big. But then again, what's happening here is you'll need to have quite a small horizontal force in order to. So if the angle is big, that means most of the angle is going to be the vertical component, and then only a small portion of the angle is going to be in the horizontal direction. And that makes sense if we are trying to, for example, if the full 80 newtons was in the horizontal direction, then this block would be accelerating at like 10 meters per second, which means that over this 2 meter distance, it would accelerate to much more than 1.5 meters per second. Okay. And yeah, let me just double check that and put my mind at ease. 5.3. Yeah, 81.42 degrees. And notice they give you options here. In the final exams, there are even more options. So that's, yeah. If you have a teacher who's particularly pedantic about which method you use and whether you show the cos 180s and all that, just remember that that's just an obstacle for you to overcome when you're in the classroom. In the final exams, you should go based on what's in the memo. Okay, 5.4. The angle between the applied force of 80 newtons and the horizontal is now decreased. What effect will this have on the work done by the same applied force when the box is moved from point X to point Y? So we just spoke about how a bigger angle reduces the horizontal component. A smaller angle would increase the horizontal component down to cos of 0, right? If the angle is 0 degrees, then the full 80 newtons is acting in the horizontal direction. That would be the maximum work that this force could do when the entire magnitude of the force is in the direction of motion. So if the angle is decreased, it will increase the amount of work. And if you were asked to explain that, you should say because the component in the direction of motion would increase, therefore increasing the amount of work done by the force, or increasing the value of F cos theta. Okay, next we've got the Doppler effect. So one of the unpopular things in this question is, again, the graphs. So guys, make sure that you learn how to read information from the graphs. The most important thing here with the and don't be daunted and like knocked back when you see a a question where the information is being given in the form of a graph, think to yourself, okay, what type of quantities do I normally need for this question? What type of quantities can I get here? Well, looking at this, we can see that we might be able to get the wavelength, right? And we're being shown that the distance for 1, 2.5 waves is 1 meter. So we'll be able to work it out from there. But let's start reading this from the beginning. A bat flies away from a stationary bat watcher at a constant velocity. The bat constantly emits sound waves at a frequency of 875 hertz. The bat watcher hears a change in pitch as the bat moves away from it. Write down the property of sound that is related to pitch. Okay, so that what they're asking there is which property of the sound waves is going to give them their pitch, and the answer there is frequency, right? So the amplitude is related to the loudness, like the height of the wave is related to how loud it is. That's how much energy the wave carries. The pitch is related, or the note that you hear is related to the frequency. That's why it's possible to have notes that are high and low pitched and are both loud or very soft. So it would really suck if that wasn't the case. Then we wouldn't be able to get really loud bass, right? In order for loud bass to be possible, you have to have a note with a low pitch, so a low frequency, but a really big amplitude. Okay. 6.2, give a reason why the bat watcher observes a change in pitch as the bat moves away from her. Okay, that is the Doppler effect. So the reason why the Doppler effect occurs is because when the bat's flying away and generating the sound, what happens is the wavefront gets stretched out, right? So the sound waves now, if the source was in one place, the sound waves would propagate normally and reach our ear at the right speed. But because the source is moving away, what that's doing is it's stretching out the waveforms, and it's making it so that now the frequency that on one side the frequency is going to be increased. That's in the direction the bat is moving, but because the bat's flying away from the observer, it will stretch out the wave and decrease the frequency. But they might just want you to say the Doppler effect. Um, they don't necessarily need you to explain the Doppler effect in terms of Huygens principle. Okay, then we've got shown below is the air pressure versus distance graph, which represents the sound waves detected by the bat watcher as the bat moves away from her with a constant velocity. Okay, so this fancy words, therefore, this is a diagram. Get some values out of the diagram, and the speed of sound in air is 340. So they want the wavelength. This is the distance given here is 2.5 waves. So to get the wavelength, we can just say lambda, which is the symbol for wavelength, is going to be equal to 1 over 2.5. And there's no real formula for that, right? I think it's 0.4. Yeah, 0.4 meters, because this was measured in meters. So that's the wavelength at 0.4 meters. There's no real formula for this. It's just the total distance divided by the number of waves in that distance. Okay. Next, determine the frequency of the sound waves detected by the bat watcher. Okay, so wavelength is directly related to frequency. We're going to say V equals F lambda. And that is, the frequency is what we're looking for. So it's going to be F equals V over lambda. And that velocity will always be the speed of sound in the medium, in this case, the 340 meters per second. And what does that give us? 850. Now it's a frequency. So what is that measured in? It's measured in hertz. Hertz are basically just cycles. Okay. And then the velocity at which the bat flies at 5 Mach. This is going to be the Doppler effect question. So let's look at the formula. FL is equal to V plus minus VL over V minus plus Vs. And you won't always see it like that times the frequency of the source. So you won't always see the minus plus, but I use this to remind myself, and you'll often see this in formulae when it's the wrong way around, right? If the objects are moving towards each other, then we put a plus on the top. If we've got a moving listener, if the objects are moving away, we put a minus away from each other, and we've got a moving listener, we put a minus on the top. So that works the correct way around, what we would expect. If they're moving towards each other, then um, you would want to add these two, right? And if they're moving away from each other, then you would want to minus these two. That's if you've got a moving listener. If you have a moving source, it works the other way around, the wrong way around. So source moving towards the listener, we put a minus on the bottom. Source moving away from the listener, we put a plus on the bottom. And so the minus plus will just help you to remember which way it works. Um, and in this case, the bat is moving away from her. The bat is the source, right? So we have a moving source. That means that VL is going to be 0. If the source is moving, then VL will be 0. If the listener is moving, then VS will be 0. If both of them are moving, and this is not really supposed to be in the grade 12 stuff, but if both of them are moving, then we use relative velocities, right? We use relative motion. What we do is we would say, okay, if this object is moving 2 meters to the left and the other is moving 3 meters to the right, then they're moving 5 meters per second away from each other. And you can treat the one as 0 and treat the other one as moving. But don't worry about that. If you haven't seen it, don't stress about it because it's not supposed to be in there. So we want to work out the velocity with which the bat flies. Which means somewhere along the way we will have been given FL, we'll be given FS, we've been given V, we know that. And then Vs is what we're trying to calculate. That's the velocity of the bat, it's the moving source. So the frequency of the listener, that's the observed frequency. We worked that out to be 850 in the previous question. Then we've got V, which is 340 plus 0 over 340. And then the bat is moving away. So minus Vs times the frequency of the source, which they told us in the question was 875. Okay, and then equation solver if you want. If you can't use the equation solver, then the best way to go here is to divide out the 875. Right. Oh, actually, maybe not. Okay. Multiply out to get rid of this denominator, 340 plus Vs. So we multiply it up to the left. On the right, we've got 340 plus 0, which is just 340, times 875. And then now we can divide out the 850, right? So in our next step, we will divide out the 850, bring it across. Right. Oops. Divide out that 850. That frees up this, because now there's nothing in front of the brackets, so we can get rid of the brackets. Then if we want to get Vs on its own, we just bring that 340 across and we subtract it. And that gives us Vs equals 10 meters per second. Calculate the velocity with which the bat flies, not the magnitude of the velocity. So it's 10 meters per second. Which direction? Is it north? Is it south? We don't know, but it is away from the bat watcher. Okay, so that's a relative direction. Right? It's away from the bat watcher. That's true. Okay, so there we've given our units, we've given our direction, everything is cool. I haven't forgotten any units so far, have I? No, I've been pretty good today. Awesome. Yeah, that's something you want to go back and double check every time you write an exam. Um, Stuff like that. Okay. Next, we've got our electrostatics, we've got circuits and electrodynamics and the photoelectric effect. So once you've gotten through the Doppler effect, you are kind of home free. I know a couple of guys don't really like electrostatics and circuits, but to me, it's actually really, really easy, um, especially the electrostatics, because you do it from grade 11, right? You do pretty much the same. And a lot of guys these days, most schools, more than half the schools, in fact, I think all the schools do EMF and internal resistance in grade 11 as well. So this is all revision for you guys. So whenever I see guys that don't like this section, I always know you don't revise enough. You don't need to study. You want to go through stuff, everything in class, but you must spend more time revising this. Okay. The diagram below shows two identical metal spheres, R and S, each placed on an insulated stand. The spheres R and S carry charges of 9 and -5 microcoulombs, respectively. The spheres R and S are brought into contact for a while and then placed 30 centimeters apart. Calculate the charge on each sphere immediately after separation. Okay, so this is really easy. This is a grade 10 formula, actually, that will often come up in grade 12. Q nu equals Q1 plus Q2 over 2. So it's just the average of the two charges, and we include the sign as well. So it's going to be 9 microcoulombs. And I didn't really bother with the 10 to the minuses here because they're in the same order of magnitude. They're both in microcoulombs. You don't have to sub them in with the units. 9 minus 5 is going to give you 4 microcoulombs over 2 is equal to 2 microcoulombs. Okay, or 2 times 10 to the minus 6 coulombs. So either one of those two answers is fine. You got to remember your prefixes, right? Milli coulombs or milli anything is times 10 to the minus 3. Okay, then we've got micro, nano, and pico. And they go in series of 3. So milli is 1,000th, right? That's divided by 1,000. Micro is a millionth. M, Greek letter M for a million. Nano, the next one that comes after a million, is a billionth. Pico is a trillionth. Okay, so it starts from M, M, Greek letter M, N, P. That's like how they came up with this. And then they are just normal orders of magnitude. So 1,000, a million, a billion, a trillion. Okay. Next, draw the resultant electric field pattern due to spheres R and S after separation. Okay. So after the separation, the resultant the resultant electric fields, those are going to be like your field patterns with the lines and stuff like that, after they've been separated, they will be like charges. So what's going to happen is the field lines are going to deflect away from each other. And it's a bit of a mission to draw them out, but let me try. So we represent the spheres as a point. And then what happens is we will have a line going backwards from sphere 1. Right, let's make that sphere 1. Let's make that sphere 2. So we can start with our median lines, just a line going straight backwards from each of them. Also, they're both positive, so the field lines will be pointing away from the positive charges. The field lines will be pointing towards the negative charges. You want to make sure that you've got the arrows in the right directions. Then what's going to happen with the rest of the field lines is they're going to bend slightly away from each other. So whereas on their own they would normally be fully radial, when you bring them together, they bend away from each other like that. And because they're equal in charge, there will be no like line connecting them, right? Whereas with if they have opposite charges, there will be a line connecting them. This is not the best, but it'll do. You can probably still get marks for this. So basically, the field lines that would be pointing perfectly diagonally here, they curve away from each other, they bend each other away from one another, if that makes sense. And yeah, then we have this gap in the middle here where there is low net electric field. So what's happening here is because these are both positive charges, they would both push a positive test charge away. And so we have directly in between them, halfway in between them, because they're equal in magnitude, we would have a net electric field strength of 0. And so the lines bending away from each other indicate that there's a lowering of the field strength, whereas when the lines bend towards each other, there's an increase. Okay. And then I see they want us to define electric field at point. It is the force that a test charge would experience at that point in space, or you can say it is the um, potential. Let's just check it out. It won't be exact with these as well. They're more and more strict with the definitions now these days. I want you to get them word for word. It's the electrostatic force per unit positive charge placed at that point. So force per unit charge, it's F over Q. Okay. Calculate the net electrostatic force experienced by T due to R and S. Okay. Now in this situation, we've got R and S. They've been in contact and they've been separated, so they both are they're both positive 2 microcoulombs. And then a third sphere of charge T a third sphere T of charge 1 microcoulomb is now placed in between them as shown, 10 centimeters from R and 20 centimeters from S. So in a situation like this, what we can do is we can work out, because it's going to experience a force due to each of these spheres, we can say that the net force that it experiences will be the sum of those two forces with respect to the signs as well. So we're going to say F net is equal to F1 plus F2. And we're going to use Coulomb's law to work out each of those forces. And we're going to pay special attention to the direction as well. So let's make right positive. I like to make right positive. Now, when we set this up, we're going to use Coulomb's law, K Q1 Q2 over R squared. And then we're going to just double check now. If T is a positive charge, that means R is going to push it to the right because R is also positive. So it's pushing it away. we will make this one, I think let's make this R on T, and then we'll make this one P on T. Remember, we're looking for the forces on T because, yeah. So the force of R on T is positive because it's to the right, but sorry, it's not P on T, it's S on T. S is going to push T to the left, so we must make it negative. And that's something that a lot of guys will get wrong. It's KQ1, Q2 over R squared. Okay, and you don't need to be super strict about this, but you can label this QR and QT, QS and QT. You've got to remember that which two charges you're looking at, and that will tell you which distance to use as well. Okay, so K is Coulomb's constant. It's 9 times 10 to the 9. Q1 is, let's see, let's make R Q1. It's going to be 2 microcoulombs. And then we have 1 microcoulomb for T. So don't try to sub in the signs here of the charges. You'll confuse yourself. You'll get it wrong. Treat all the charges as positive and then decide which direction the net force is going in, right? Decide which direction the force is going in. So even if one of these was negative, I wouldn't sub it in as a negative. What I would do is I would sub them all in as positive, and I'd say, okay, like let's say, for example, S was negative, then I'd say S is pulling T to the right, therefore its overall sign is positive, right? So you decide whether each force is positive or negative, depending on which way the force would act. And you sub in all the magnitudes of the charges as positives. That's how we do it. 1 microcoulomb. And then the distance is 10 centimeters. Don't forget to change to meters. It's 0.1 meters. And we square that. Okay, the magnitude of charge S is the same. Magnitude of charge T is the same. And then we've got a distance of 20 centimeters. And that's going to give us a big, long answer. Now you can work each of these out separately, right? You can work each of these out separately. And then just subtract them at the end. It's up to you. One is more quick and efficient. The other is safer. Time is a big factor in the exams as well. So you've got to take some risks to save some time so that you have time to figure things out later on. Otherwise you lose out by rushing. And we get 1.35 points. And our answer is positive, which means that it is to the right. So far, I haven't had to rewrite my answer, but if this came out negative, I wouldn't be leaving my answer as a negative. And I'm telling you, I don't know how many times I have to say this to guys, and they'll still just, it just goes in one ear and out the other ear. If your answer is negative, you rewrite it as a positive, and then you give the direction if they have not set magnitude. So what did they say here? The net electrostatic force. The electrostatic force will have a magnitude and a direction. So unless they say the magnitude, then you're definitely going to need to give a direction. Either way, you never leave your answer as a negative. You give your direction in words. Next, define the electric field at the point. We've done that. 7.5, calculate the net electric field at the location of T due to R and S. Okay, so if you want to go and use this formula, like the same way we forces, then you will be wasting time. You will be wasting time. Okay, and that is because like you'll basically end up doing this whole calculation again, whereas you can just use this formula, E equals F over Q. Now we've got, because that was the definition, right? Electric field is force per unit charge. Now the force that it's experiencing is 1.35 newtons, and the size of the charge is 1 times 10 to the minus 6, or 1 microcoulomb, and that is going to give us 1,350,000. And what is this measured in? It's measured in newtons per coulomb. Newtons per coulomb. Okay. Now you can also change that to 1.35 meganewtons per coulomb. But yeah, don't don't change your answer and bring in scientific notation unless you have to. You're just introducing more places for yourself to make an error. Okay, we're making good time, guys. I don't know. I'm not going to try and get through everything today. Um, we've done a pretty good run so far. Haven't received any questions yet, or any. I haven't really received any submissions. So yeah, I think I'm going to call it a day for today. I've also been unwell, so but please, I would encourage you guys, send through submissions, even if you do it during the week. Then I can go through them during these weekly sessions, and you can come check later. I see that there are some guys that are watching during the week and not necessarily during the live stream. But yeah, I don't know what's happening. Are you guys not like getting ready for exams? Or are we, yeah, just watching other stuff? That's fine. Um, anyway, see you next week, and thank you for tuning in.